Swayam Prabha. Digital India. Educated India.
Okay, so I guess we'll get started, right? So in yesterday's class we started off with frequency response, right? So frequency response essentially is used to denote the response of systems to sinusoidal inputs, right? So that's what we started off with. And as far as frequency response is concerned, like we saw that one important property of linear time invariant systems is that, like, let's say we give a sinusoidal input of frequency omega, the steady state output is also going to be of the same frequency omega, but the magnitude of the input is going to be scaled by the magnitude of p of j omega, p of s being the Planck transfer function, and the steady state output is going to be a sinusoid, but it's going to be shifted in phase by phi. Phi is also the phase of p of j omega, right? So depending on omega, the magnitude and the phase shift would be different, right? But that's something which we observed yesterday. So consequently, the frequency response is characterized by p of j omega, which is called as the sinusoidal transfer function, right? So that's something which we discussed yesterday. And the question that arises is that, like, since p of j omega is going to be what is a complex valued function of omega, right? How does one visualize it, right, as omega is varied from a practical perspective, right? So for that, like there are multiple visualizations that are possible. The most commonly used one, or the one that we are going to commonly use, is what is called as a Bode plot, and there is something called as a Nyquist plot and also a Nichols plot. Okay, so let's get started with the Bode plot today, and then, like, we'll see what we do when we use the Bode plot, right? First of all, how to plot the Bode plot, then once given a Bode plot, how do we interpret system characteristics from that plot. Okay, so those are aspects which we are going to study now. Okay, yeah. So what is this Bode plot, right? So we know that p of j omega has two components, like one is the magnitude and another is the, and another one is the phase of p of j omega, right? So that's going to be the two components, right? So it has a magnitude and a phase. So please note that both the magnitude and phase are functions of omega, right? So then in the Bode plot, what we do is that there are two plots. Okay, the first one is what is called as a magnitude plot. Okay, so what is this magnitude plot? In the magnitude plot, we plot omega on the abscissor and the magnitude of p of j omega on the in the ordinate. Okay, but the important thing to note is that, like, we use a logarithmic scale for omega on the abscissor, okay, or the horizontal axis, and this p of j omega is plotted in decibel measure, right? So how do we get the decibel measure? So given a p of j omega, like, we take its magnitude and then we take the logarithm to the base 10 and then multiply it by 20, okay, to get the equivalent magnitude in decibel units. Okay, so that's what we do. Okay, so now the question arises, like, why do we do this, right? So what do you think is the difference between a logarithmic scale and a linear scale? Like, see, most of us are exposed to a linear scale, right, while plotting, right? So what is a logarithmic scale? Let's say if I use omega, on the if I plot omega on the x-axis, using a logarithmic scale, right? How can I characterize it? No. Let us say, like I have 3 points, right? So let's say, like I have omega 2, omega 1, omega 3, right? So the distance between omega 1 and omega 2 is the same as the distance between omega 2 and omega 3. So now if I use a linear scale, like what can I say about the distance between these two sets of points? Yeah, they are equidistant, but what does it characterize? No. One of them is
10 times the other.
10 times. No, if I use a linear scale. Linear scale, if these 3 points are equidistant from one another, that is omega 1, the distance between omega 1 and omega 2 is equal to the distance between omega 2 and omega 3. What does it mean? No. Yeah, so if I use a linear scale, right? So what it means is that omega 2 minus omega 1 is going to be equal to omega 3 minus omega 2, right? On the other hand, if I use a logarithmic scale, what can I interpret? So these are equidistant, right? So the distances are equal. So if I use a logarithmic scale, the ratios are going to be the same, right? So if I use a logarithmic scale, omega 2 by omega 1 is going to be equal to omega 3 by omega 2, right? So now on the Bode plot in the x-axis or the abscissa, right? So we essentially use a logarithmic scale, like of course we use to the base 10, right? And then what happens is that if I have 3 points which are equidistant from one another, this property is going to hold, okay? And as he told, like if you have like a point, essentially 2 points, in a certain sense, like we'll plot it, like we'll say that one point is 10 times the previous one, and that's how we will define what is called as a decade, right? So we'll come to that, okay, shortly. So but then why do we use a logarithmic scale? Why do you think like one should use a logarithmic scale instead of a linear scale? Sorry?
There is too much variation with omega. The variation of mod of p j omega is not repeating, or you can see variation over a vast space.
Okay. Yes. One point is that like you can essentially plot a wide range of omega, right? See, for example, like if I use a logarithmic scale, let's say like I want to plot omega, okay, what I can do is that like I can start with, let's say, 0.01, okay, I can call this 0.1, I can call this 10, I can 1, 10, 100, let's say 1000, you get the point, right? So and then I can go to 10,000 and so on, right? So you can see that like in a finite scale, I can cover a vast range of omega, right? At the same time, like if I use a linear scale, it's going to be really difficult, right? So essentially to plot such a vast scale, okay? And more importantly, you can, so the first thing is that you can cover a larger range of omega. And what is the second advantage that you can see? You can see that you can also expand the low frequency range. Like by and large, like in many applications, practical applications, you will see that the low frequency range is also of equal importance as the high frequency. Okay. See, for example, if you use a linear scale where 1 unit is 1 radians per second, okay, you go from 0, 1, 2, 3 and so on, right? So 0.1 is going to lie between 0 and 1. 0.01, if you want to plot, it's going to be very difficult in a linear scale, right? On the other hand, in the logarithmic scale, you can really expand the low frequency region, right? So the low frequency region can be expanded, right. So that's something which is also of interest to us. Of course, what is the limitation with the logarithmic scale? High frequency gets shrunk, but you can see that I can't plot 0, right. So see, on a linear scale I can mark a 0, here I can start from 0, but that's okay, like see, because see, practically we are looking at frequency response, right. What does it mean by giving a 0 frequency signal, right. So that means that sin omega t or cos omega t, if I say omega is 0, I am going to get either a 0 or a 1, right. That doesn't make sense for me, right, because I want to see sinusoidal inputs, right. But so that's okay, it's not a very serious limitation as such, right, as far as a logarithmic scale is concerned. So that's why we have we use a logarithmic scale on the abscissa for the frequency. Now comes the second question as to why we use a decibel scale for the magnitude, okay, because we take the magnitude, right. We take the logarithm to the base 10 and multiply it by 20 and convert it to decibels, right. Why should I use a logarithmic scale for the magnitude? Same reason, right, similar reasons would apply, right. So I can cover a larger range of magnitudes in a finite scale, correct. See, the plant transfer function can have a wide range of magnitudes, so I can cover a larger range. I can focus on lower magnitude values also, right, that region is also going to be expanded. So can you also like sense any other advantage, of using a logarithmic scale? Let us say if P of j omega, let us say is P1 j omega times P2 j omega divided by P3 j omega, let us say P1, P2 are some factors, right. So what happens if you use a logarithmic scale? So if you then do log of P of j omega, what happens is then, of course, to the base 10. So we are just going to get log to the base 10 P1 j omega plus log to the base 10, this is going to be the magnitude, okay, log to the base 10 magnitude of P2 j omega minus log to the base 10 magnitude of P3 j omega, right, that is what we are going to get. So consequently you can immediately observe that if you have a basically product and ratios of factors, right. So what you are going to get is that, like, once you take the logarithm, they become the algebraic sum, right, of the individual factors. So that's a pretty good advantage which would exploit, right. So we will see that you give me a transfer function, I break it into smaller terms. What I do is that I plot the magnitude plot of the individual terms, then I just add or subtract, okay, like as the case may be, right. So that way, like I can plot the Bode plots pretty easily, okay. We are going to see how that is going to help us shortly, okay. Yeah. Similarly, you can see that the phase of P of j omega is also going to follow a similar trend, right. So we will see that it is going to be phase of P1 j omega, phase of P2 j omega minus phase of P3 j omega, right. So essentially, if you can divide basically break down a given transfer function into simpler building blocks, which we are going to look at, then what we do is that, like, we just plot the Bode diagrams of the individual blocks and then take the algebraic sum, okay, that is it, okay. So then we are done, right. So that is a very a good advantage of using a logarithmic scale, right, even for the magnitude. So now the second plot is what is called as a phase plot, okay. So this Bode plot has two plots, okay. First is the magnitude plot, okay. Second is the phase plot. So what is the phase plot? In the phase plot, once again, omega is plotted on the abscissa, so using a logarithmic scale, okay, and the phase of P of j omega is just plotted in degrees using a linear scale, okay. Here we just use a linear scale, okay, like there is no need for any logarithmic scale here, okay. You calculate the phase. So anyway, phase of the complex valued function satisfies this property, right? So we don't need to take logarithm as such, okay? We just use a linear scale for that, okay? So that's what the phase plot essentially would visualize, right? So essentially what happens is that the Bode plot has two plots, the magnitude plot and the phase plot. The magnitude plot essentially plots the magnitude of the sinusoidal transfer function in decibels versus omega on the x-axis or the abscissa using a logarithmic scale, and the phase plot plots the phase of the sinusoidal transfer function in degrees versus omega, once again on a logarithmic scale on the abscissa, okay? So that's what happens with the Bode plot, right? So as I just discussed, like one advantage of doing this way is that like you can really use certain building blocks. If we learn how to plot the Bode diagram for the building blocks, it's easy to plot it for any particular transfer function, right? So what do you think are the potential building blocks? What I called as building blocks, okay, let's say within quotes. So essentially these are the basic factors which can make up a transfer function, right? Think about whatever we have discussed till now, right? So what are potential factors that can come? See, we can have a constant, right? A transfer function can have some constant k, right? So it can have a integral term 1 by s, right? It can have a derivative term s possible, right? So then what else? It can have a first order term of the of the form 1 by ts plus 1. It can also have ts plus 1, right? So I am just writing down what are all the potential factors that can appear in the numerator and the denominator, right? And we can also have a complex conjugate factor, right, of the form omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared, right? So we can have such a term, right, which second order factor which cannot be factorized into real factors, right, in the numerator. Same way I can have a second order factor in the numerator, right, of the transfer function in this way, okay? So these are all potential factors. So you can see that. Yes. Can I change the color? Okay. So so essentially, like we can have a constant, we can have 1 by s, right? So which is like an integral, s which is like a derivative, like, and then I can have 1 by ts plus 1, and then ts plus 1 in the first order factors, like that's what we are looking at, and we can have second order factors with complex conjugate roots of this form, both in the denominator and the numerator, right? So we can have all these factors, right? So now you can immediately observe that I can essentially rewrite any transfer function in this particular form. We will see how to do that, right, as we go along, right? So but these are the basic building blocks that we are going to look at. So if we understand how to plot the Bode diagram for each of these building blocks, then we are done, right? So that's what we are going to look at, okay? So let's understand how to plot the Bode diagram for these blocks, okay? So let me start from the first block. So let me consider, of course, let me use the term symbol g of s, okay, to say that it's any generic complex valued function, okay? So anyway, k is a real number, so of course k is greater than 0, otherwise I can't take logarithm, right? So let's say like k is greater than 0, and then like we essentially look at this one, okay? So now what happens if I want to plot the Bode diagram? Okay, if g of s is k, g of j omega is going to be just k, right? So that's it, okay? So then what will happen? The magnitude of g of j omega is going to be equal to 20 log to the base 10 magnitude of k, which is just k in decibels. Okay, so or of course k need not be. Let's put a generic case. Okay, let's say k is some real number. Okay, so right, let's do this. Right, yeah.
So we haven't covered the case where Ts plus 1 instead of when there is some other constant. Why have we not covered that?
I didn't get you. I'm sorry.
We have covered Ts plus 1. But instead of 1, there can be some other constant.
Absolutely. We are going to see how to rewrite. Okay, that's something which I'm going to show you. Right? Okay, good point. He is saying, why don't you consider 1 by s plus a, for example? You can have factors like this. You know, like how come you are making the constant term as 1? Okay, you can see that you can always rewrite a given transfer function in this form. I am going to show it to you. First, let's learn the building blocks, then we will do examples. Right? So, where you can easily rewrite in this form. Right? So, let's say we essentially take k to be some real number. So, g of j omega is going to be k, and magnitude of g of j omega is going to be 20 log to the absolute value of k in decibels. What can you say about the phase of g of j omega? It is going to be 0 degrees if k is greater than 0. It is going to be 180 degrees if k is less than 0. Right? Why? Because if I essentially plot the complex plane, okay, what I call as a g of s plane, okay, because I am plotting this factor. So, let us say, you know, like if I have k to be positive, you can immediately see that the phase is 0, right. On the other hand, if let us say, you know, I consider a k2 which is negative, you can immediately see that the phase is going to be 180 degrees, right. So, it really depends on the sign of k. Okay. So, now if I want to draw the magnitude plot and the phase plot, what is it that I should do? So, you can see that if I draw the magnitude plot and the phase plot, so I plot it in decibels, okay, and the phase plot also in decibels. Sorry, the phase plot also where the phase is in degrees. Okay, so what's going to happen to the magnitude plot? The magnitude plot, you know, like I'll just have a straight line with respect to omega. That's it, right? So where this value is going to be 20 log to the base 10 of k, correct? So in the phase plot, I will have either 0 if k is less than 0, or see, typically what we do is that, like, we take a negative value, okay, we will see why we do that, okay. So we take it as minus 180, okay. So typically we will take it as minus 180 if k is less than 0, okay. I will explain why we take the negative value here, okay. So later on, fine, yeah.
Magnitude of g j omega as equal to 20 log.
Yeah, so that's the in decibel units.
Equal.
It's basically, it's understood that, you know, like you are writing in decibels, or yeah, if you want to be very particular, if you say 20 log to the base 10 magnitude of g of j omega is this one. Okay, fine. So okay, I got your point. So let's say I write the magnitude of g of j omega as absolute value of k. So then the 20 log to the base 10 magnitude of g j omega in decibels is going to be 20 log to the base 10 absolute value of k. Fine. Okay. So that's going to be the Bode plot for this one, right? This constant term. And see, typically what happens is that, like, we take frequency ranges on the abscissa, which are typically here it doesn't matter, but we essentially use, you know, like what is called as a decade. Okay, by convention, you know, like we plot frequencies, or we mark frequencies which are a decade apart, right? What is a decade of frequency? See, a decade essentially means that You are at a particular frequency, you are considering a range from that frequency to either 10 times that frequency or 0.1 times that frequency. Okay. So, let us say what is a decade? At a given frequency omega, okay, the range omega to 10 omega is 1 decade above omega. Okay. Okay. Similarly, the range 0.1 omega to omega is called as 1 decade below omega. Okay. So, that is the definition, okay, of this. So, typically by and large, you know, like we will plot frequencies, I would say we will mark on the x-axis, you know, like as decades. Okay. So, you can see that if you consider 1 as the base frequency, right, the frequency under consideration, 10 is 1 decade above 1. Okay. So, the region 1 to 10 is a region 1 decade above 1, right. From 0.1 to 1 is 1 decade below 1. Okay. So, that is what this is. Okay. So, of course, this is a, I will say a frequency range, right. So, 10 omega is going to be 1 decade above omega. Okay. So, oops, sorry, if I have to be very correct. So, 10 omega is going to be 1, but typically it is illustrated as a range. So, let me keep it this way itself, right. So, but you get the point, right. So, if you essentially consider a frequency omega, 10 omega is 1 decade above omega and 0.1 omega is 1 decade below omega, and by and large it is considered as a range, right. Okay.